Union by rank in disjoint set. Union by rank is a technique used in disjoint set data structure in order to improve the performance of find and union operations. In the last lecture, when we learned in detail about disjoint set data structure, we learned that there are two primary operations that we generally do in disjoint sets. One is find operation and the other is union operations. What did we learn about the time taken by these operations? Coming to the find operations, we had seen it takes order of n time. And what about the union operation? That also took order of n time. So what we are going to do now is, using the rule of union by rank, we are going to improve the performance of find and union operations. That is, we'll bring down the time complexity of both these operations. This is what we are going to do in this lecture. First of all, what is this rule of union by rank? This rule is applicable whenever you perform a union operations. So whenever you do this on union operation, automatically your time complexity of find is going to come down. In case of union operation, how did you perform a union in the last lecture? Whenever you wanted to perform a union, you arbitrarily chose any among the two trees. Let us say you have two sets, set 1 and set 2. These two are disjoint sets. And you have a tree corresponding to set 1 and a tree corresponding to set 2. What did you do? You arbitrarily chose any among these two and made it point to the other. That is, the representative of one tree was made to point to the representative of the other tree. This is what you did. And this choice was purely arbitrary. That is, either you made this one point to this or you made this one point to this. And because of this, we had seen that the time complexity of find and union went to order of n. This time we are going to apply a rule on this union operation and this will improve the time complexity. Let us see what is the rule. The rule says, the union by rank rule says, whenever you want to perform a union operation, always attach the smaller tree to the larger tree. That is, you should take the representative element of the smaller tree and you should attach it to the root of the larger tree. Then the question is, how do you decide which is the smaller tree and which is the larger tree? Because there are many different criteria that you can use in order to say one is smaller and the other is larger. Maybe you can say one tree is larger in height and because of it, it is larger. Or someone else may say this tree has more number of nodes and because of it, it is larger. In this particular case, in case of union by rank, in order to decide which is smaller and which is larger, we have a new concept to be introduced that is called rank. Based on the rank of the tree, you will say which is smaller and which is larger. The tree which is having a larger rank is larger tree. The tree which is having a smaller rank is smaller tree. One question is, what are you going to get by attaching the smaller tree to the larger tree? What you're going to get is, by doing this, you prevent the tree from becoming too deep. That is, in the previous case, when we did union in the last lecture, we had seen that sometimes the tree went too deep and this increased the depth of the tree. This time, when you are applying this union by rank rule and you attach the smaller tree to the larger tree, you will create a balance for the tree. And because of this balance, your find operation will be efficient. That is, the tree won't grow too deep. And because of that, the tree will stay balanced. Okay. So the next thing you want to understand is, what is this concept of rank? What exactly is rank? And how can you determine the rank of a tree, right? So rank, it is an upper bound on the depth of a tree. So rank is not exactly the same as depth, but it is an upper bound on the depth, which means rank says your tree can never grow larger than this. Whatever is the rank, that is the maximum depth possible for your tree. This rank generally it will be close to the actual depth of the tree, but especially when you use path compression technique, you will see that the actual depth of the tree and the rank of the tree will differ. In the next lecture, we'll see what is path compression, and at that point you will see that path compression will flatten the tree, and even at that point rank will tell you what is the worst possible depth. Okay, so rank is not same as depth, but rank is an upper limit on the depth of the tree. So you can see rank as a heuristic. This heuristic is used to keep the tree balanced. Okay, whenever you are performing union, this heuristic helps you keep the tree balanced. Next question is, how will you determine the rank? How will you say this is the rank of a tree? Initially, you will say that all your trees are having rank 0. Why all your trees? All your trees means in the initial situation, every single element will be its own tree. We had seen this in the last lecture. If you have an element 0, it will be its own tree, its own disjoint set, and 0 will be pointing to itself, which means 0 is the representative element itself. This means the rank will be 0. Similarly, every element will be its own representative element. It will be its own tree, and the rank will be 0 to begin with. How do you increment the rank? Whenever you want to perform a union operation, you will see one thing. You will see whether both the trees are having equal ranks. If the rank of both the trees are not equal, in that case, you are not going to increment rank at all. Whatever is the rank of both those trees, you are not going to touch that. And what are you going to do? When you are going to do the union, you will attach the smaller tree to the larger tree. But you are not going to change the rank. You are simply going to take the smaller tree, that is, whichever tree is having a smaller rank, and you are going to attach it to the larger tree. But in case the ranks are equal, in case both the trees are having equal rank, then you don't have a smaller tree and a larger tree because both are of the same rank. What will you do then? In this case, the choice is arbitrary. You can arbitrarily choose any one tree to point to the other. But once you make this choice, you know one tree is going to be the parent and the other one is going to be the child. So whichever is the parent, for that tree, you are going to increment the rank by 1. So whichever is chosen as the parent, for that tree, you will increment the rank by 1. So how is the rank getting incremented? Only during union operation. If both the trees are having the same rank, this is the only case when the rank of a tree will get incremented. So at any point, you will know what is the rank of any tree, right? Tree means a disjoint set. So I am referring to tree because disjoint set, we are representing it using a tree. About this, we had learned in the last lecture. What we will do now is, we'll take an example that is the same example that we took in the last lecture, and we'll see what is the difference that is brought in by the concept of union by rank. We'll take the same set of disjoint sets and we'll perform the same set of operations. Let us say you have these disjoint sets with you. You have 0, or let us say I'll start with the arrays. In the last lecture, we had seen we had a parent array. And what is this parent array used for? Using this parent array, you were able to keep track of all the sets. I had told you that you don't need any other data structure here. Just a single parent array will help you keep track of all the elements that you're having, all the disjoint sets you're having. So in the last lecture, we had seen how that is done. This time, one is that you have this parent array, 1, 2, 3, 4, 5. You have 5 entries, 0, 1, 2, 3 and 4. So these are corresponding to 4 different disjoint sets that we are having. Similarly, you also have a rank array. So last time in the last lecture, we only had the parent array. This time, you should also have a rank array because you want to keep track of the rank of all the elements, right? 1, 2, 3, 4, 5. So this is your rank array. This time these two arrays are going to keep track of all the operations. Okay. Let us first see which are the different elements. One element is 0. So at the initial stage, each element is its own tree. It is its own representative element. So it will be pointing to itself, right? 0. Then you have 1. 1 is also pointing to itself. Then you have 2. 2 is also pointing to itself. So at this point, all these are their own representative elements. That is what it means. Then you have 4. This is the present scenario. And what are you going to have? Now you are going to perform different operations. First of all, let us initialize the parent array and the rank array. What is the parent array? Parent of each element is that element itself. So parent of 0 is 0, parent of 1 is 1, parent of 2 is 2, parent of 3 is 3, and parent of 4 is 4. What about the rank? I told you that at initial position, rank of all the elements is 0. So all of them are having 0 as the rank. What should we do now? Let us say you want to do a union operation. You want to do union 0, 1. We did this in the last lecture as well, but this time see the difference brought in by union by rank idea. Okay. So let us do union 0, 1. What are the steps? First you will do find of 0. How will you do find of 0? You will go to the parent array. You will check who is the parent of 0. Parent of 0 is 0 itself. So what will you do? Whenever the parent is that element itself, that means it is the representative element. So you found what you are trying it. The representative element is 0. What about find of 1? When you do find of 1 in this parent array, parent of 1 is 1 itself because the entry in 1 is 1 here, right? Because of that, your find operation, it's supposed to find 1 only because the representative element of the set having 1 is 1 itself. What will you do now? When you found both the representative elements, this time you have an additional thing to do. You can't arbitrarily make one point to the other. Instead, you have to see what is the rank of each of these representative elements. So keep one thing in mind. This concept of rank makes sense only when we are talking about representative element of the set. When it is not a representative element, then you don't care what is the rank that is there in the array. So whenever you are populating the rank in this array, only thing that is of value is the rank of representative elements. So whenever we are updating, we'll only be concerned about the correct rank of representative elements. If it is not a representative element, then we don't care about whatever rank is put here. Okay. So what is the rank of 0? If you see in the rank array, rank of 0 is 0. And what is the rank of 1? Rank of 1 is also 0. So what happened here? Both the trees are having the same rank, which means there is no option for you to attach the smaller tree to the larger tree. What will you do? You will arbitrarily attach any to the other, and then whichever becomes the parent, you have to increment the rank of that parent. So we have 0 and 1. Let us say we want to attach 0 to 1, which means 1 will stay as the parent. So 1 will stay as the parent. 1 is the parent. And what will you do? You will attach 0 to 1. This is what you did. You could have done the other way as well because here rank of both was same. And what do you have to do? You have to update rank of 0 in the parent array. So rank of, parent of 0 in the parent array. Parent of 0 is now 1. Okay. Parent of 1 is 1 only. So parent of 0 is updated. What about the rank array? In the rank array, you have to increment the rank of the parent. So parent is 1. Its rank is presently 0. You will increment it and make it 1. Okay. So two operations, when you are actually writing the code or implementing it, only two changes are to be made in order to do a union operation using union by rank. One change is change of one element in the parent array, and the second one is change of rank of one element in the rank array. Just with two operations, you will be able to do union operation in this particular data structure. Let us say after this, you want to do one more union operation. The same thing that we did in last lecture. Let us say you want to do union of 2 and 3. So 2 and 3 are what you want to find union. So first you will do find operation on 2. So you will check the parent array. What is the parent of 2? It is 2 itself, which means the representative element is 2. Next is find of 3. When you do find of 3, you will understand that in the parent array, parent of 3 is 3 itself, which means 3 is the representative element of the set containing 3. Next step is to find the rank of representative elements. What is the rank of 2? In the rank array, rank of 2 is 0 and rank of 3 is also 0. So again you are in a situation where both the elements are having the same rank. Because of that, you can arbitrarily choose any of these to point to the other. So let us say we are going to choose 2 as the parent. So we are choosing 2 to stay as the parent. If we choose 2 as the parent, 3 will point to 2. So 3 will be pointing to 2 now. In this case, what are the changes that you have to make in the array? In the parent array, parent of 3 has to be modified to 2. And what about the rank array? In the rank array, rank of 2, which is the new parent, will be incremented. So rank of 2 was presently 0. Now you will increment it to 1. So rank of 2 is incremented to 1. This is the change after union operation. Let us do one more union, which is union of 3 and 4. So we are following the same steps as the last lecture because I want you to see what difference union by rank is going to build. So till this point, there is no major difference, but from here on, you will see that union by rank idea, union by rank method is going to bring in some changes. So when you do union of 3 and 4, what happens? You have to do find of 3. Find of 3, you will check in the parent array. Parent of 3 is 2. Then you will check the parent of 2. Parent of 2 is 2 itself, which means that representative element is 2. So 2 is the representative element. What about find of 4? You know parent of 4 is 4 only. And these things you can see from here as well. In the illustration you can directly see. But I am trying to find it from the array so that you understand how it internally works or how it is supposed to internally work. Okay. Otherwise you can simply see at this illustration and understand. I am keeping this illustration so that you understand what is happening. And I want you to look into the array and understand how it is implemented. Okay. So parent of 4 is 4 itself. So representative element is 4. Next step is you have to see the rank. What is the rank of 2? From the rank array, you know rank of 2 is 1. What about the rank of 4? Rank of 4 is 0. Because of which rank of 2 is larger and hence the tree with representative 2, this is larger tree, and the tree with representative 4, this is smaller tree. So what will you do? You will take the smaller tree and you will attach it to the larger tree. So how will you do that? You have to attach 4 to the larger tree. So let us say your 4 got attached to the larger tree. And what changes should you make in the parent and rank array? Parent of 4 should be updated to 2. So parent of 4 is updated to 2. What about the rank array? Because you had a smaller tree and a larger tree, you are not making any increment on rank. Rank increment is supposed to be done only when both the trees are having equal ranks. So in this case, because one tree had rank 1 and the other had rank 0, you are not going to change rank at all. So there is nothing to be done in the rank array. So we are done with this union operation as well. Let us do one more union which we did in the last lecture. So you will see how the tree is growing here. Let us say union of 0 and 2. What will you do first? You will do find of 0. When you do find of 0, parent of 0 is 1. Then what is the parent of 1? Parent of 1 is 1 itself, which means 1 is the representative element. When you do find of 2, you check the parent of 2. Parent of 2 is 2 itself, which means 2 is the representative element of this set. And you can see the same here. When you see this particular tree, 1 is the representative element. And for this tree, 2 is the representative element. So you know the representative element of both. Let us see the rank. What is the rank of 1? Rank of 1 is 1. And what is the rank of 2 in the rank array? Rank of 2 is also 1. Now if you see these trees, it seems like this tree is larger and this tree is smaller because the number of nodes are different. This tree, which is having 2 as the representative, have more nodes than the other one. But both are having the same rank, because of which we don't have a smaller tree and a larger tree. So both the trees are of the same rank. What will you do? You can arbitrarily attach any of the tree to the other tree. Let us say you want to attach this one to the other. Okay, so your 1 will stay as the parent. This is the tree, and your 0 is attached to 1. And what about this tree? You are going to make its representative element, which is 2, to point to 1. So 2 will be made to point to 1. What about 3 and 4? 3 and 4 will stay here. 3, 4. Okay. And one more thing to keep in mind, even though all these look similar to binary trees, in case of disjoint set, there is no such rule that you should have a binary tree or a ternary tree. You can have any number of children on any nodes. Here, when we took this example, it automatically happened that the trees look like binary trees. But ideally, when you work with disjoint sets, you will have trees which are having any number of children. Okay. Especially in the next lecture, when we see path compression, we'll see that same node will have a lot of children. Okay. So this is the tree that you found. And what about the updation in parent? Parent of 2 is to be updated. So I'll update parent of 2 as 1. So 1 is the new parent of 2. And what is the updation to be done in rank array? So this time both were of same ranks and we made 1 as the parent, which means rank of 1 should be incremented. Rank of 1 is presently 1. We'll increment it to 2. Okay. So this is the final parent array and the rank array that you have. And illustration wise, this is how your disjoint set will look. The next question is, what improvement were you able to make in case of time complexity of find and union operations in this case? This is what we have to understand. Let us understand this in detail. What is the improvement that is brought in? In order to understand, first thing you want to see is in case of find operation, what is the time complexity dependent on? In case of find, let us say you want to do find of 3. What will you do? You will go from the point where 3 is there till the root of the tree. That is till whichever is the representative element. That is how you will find the representative element and return the output of find operation. So in worst case, you may have to travel from the bottom of the tree till the root of the tree. So the maximum operations you require is same as the height of the tree or the depth of the tree. So your time complexity of find operation is determined by the depth of the tree. In the last lecture, when we did not apply union by rank, in that case, maximum depth possible in worst case was order of n. That is why your find operation was order of n. So this time, let us see what is the maximum depth possible. Coming to this rank concept, whenever two trees which are of rank k, when these are merged, both are having the same rank k, what will happen? The resulting tree will be having a rank of k plus 1. So what we have to understand is, when you are incrementing rank by 1, 1, 1 and so on, what is the maximum rank possible when you have a total of n nodes in the tree? This is what we want to understand. So in order to understand this, we want to understand what happens during this merging. Whenever you are merging, let us say two trees which are of rank k, what happens? the number of nodes in the tree gets multiplied by 2. So when I say this, you may ask, it need not always multiply by 2. It may so happen that one tree is having lesser nodes and another tree is having more number of nodes. In this case, it is actually not getting multiplied by 2. But the actual answer is, it is getting multiplied by 2 and maybe even more. Whatever is this, there is extra, that is additional. But whatever is the minimum required size, that is getting multiplied by 2. And the reason is, whenever you have a rank of k, then that tree will have at least, bare minimum, it will have 2 power k nodes. You can check this with any tree. If it is having rank k, it will be having at least 2 power k nodes. Which means, if you are taking 2 nodes of rank k, both of them will be having at least 2 power k nodes. Which means, the new updated number of nodes will be at least 2 power k plus 1. That is 2 power k into 2 power k. Which means, you are having 2 power k and 2 power k. So you will be doing 2 power k plus 2 power k. So it will be 2 power k plus 1, which same as 2 power k into 2. So ideally, you are already having a multiplication by 2. So you can think like this. At least the number of nodes is getting multiplied by 2. Okay. And if this is the case, then what is the maximum height possible? At each step, you are multiplying by 2. So you are doing it like 2, then 2 power 1, 2 power 2, 2 power 3, so on. Maximum rank, let us say, is 2 power k. And in order to reach 2 power k, you have a total of n nodes, which means with n nodes, if you are having a rank of 2 power k, then the maximum rank possible is log n. That is, in log n steps, you will be reaching this particular kth rank if this is the case. So log n is the maximum possible rank. And what is a rank? Do you remember at the starting when we discussed about rank, we told that rank is the maximum or the upper bound of the depth of the tree. So we said that rank is the maximum possible depth for a tree. So rank gave you the upper bound on depth, which means the upper bound on depth is now order of log n. Depth may be smaller, may be very small, but worst case, you can have a depth of order of log n in the tree when you are having union by rank. And what will this tell you? This will tell you that if you want to go from the bottom of the tree till the root of the tree, maximum number of steps to be taken is order of log n, which means the time complexity of your find operation is order of log n. And what about the union operation? Union operation has 2 find operations and then a merge operation. And what about this merge operation? You just have to update one particular index in the parent array, which means this is an order of 1 operation, whatever is your merge operation. So the main time consuming operation in case of union is find only. So whatever is the time complexity of find, which is order of log n, that is going to hold as the time complexity of union operation as well. So with the technique of union by rank, your time complexity of find operation is order of log n, and that of union operation is also order of log n. In the next lecture, what we'll do is, we'll see something called as path compression. So when path compression is applied along with union by rank technique, we'll see that the time complexity will come down to constant. So this is our final aim. We want a constant time complexity for both find as well as union operations. In the next lecture, we'll see how this is done using path compression technique.